Hi, folks, here we go. We're going to talk about a history of gravitation. Now, I will make this slideshow available to you as well. Um, so you might want to actually stop this, print the slides if you'd like to take some notes on the slides as we're going along, because although the slides have some text on them, there is additional information that you're going to want to have. So the slides aren't overly text-filled, just with some key bullet points. So what we're going to talk about here is how the idea of the law of universal gravitation came to be. And to understand that, we need to understand a bit about the history of astronomy through the ages. So that's our goal here. So we're going to walk through an idea. And that idea just starts with a notion of, well, I would posit that astronomy was crucial for the development of all ancient civilizations, that without a study of astronomy, there would not have been large ancient civilizations. So why do I say that? I say that because astronomy served three critical purposes for ancient civilizations. So what are those three purposes? First, purpose was agriculture, right? The calendar. It's impossible to have an agricultural cycle if you don't have a calendar. For example, in Egypt, if you did not know that when Sirius, the dog star, was 5 degrees above the horizon at a certain time of the day, that you had to get the hell away from the Nile, you had a lot of problems because the Nile would flood. Right, and so the push and pull of the calendar was important for understanding large scale agriculture. So without agriculture, you have hunter gatherer societies. You don't have civilizations where you can settle in and expand to empire and to large scale civilization. So astronomy was really useful for creating the calendar. We'll look at some examples of that in a minute. Next, navigation. Right? The stars are used for navigation all the time. During the day, we use the sun for guidelines, and night, the stars. Navigation was really important. If you had an ancient civilization and you had multiple cities in your ancient civilization, you had to know how to get from one to the other, right? Navigation and exploration were critical for forming large-scale ancient civilizations. And finally, and most importantly, actually, religion. A very important existential question is why? People look to the heavens to answer the question why, and they created religions that were largely derived from the stories that they told themselves about what was happening in the heavens to explain their world around them. And the reason why religion, in my mind, is super important is because it provided a sense of social order and social cohesion. It's hard to have a society if there's not a guiding ethic, and religion formed that guiding ethic, and most ancient religions were derived in some way, shape, or form, or inextricably linked to the notion of astronomy. Now, that's going to become problematic later because the stories that we tell about religion become the stories we tell about astronomy, and therefore, to challenge astronomical norms is to challenge religious norms. And that becomes a critical tension throughout the ages. So, astronomy necessary for the development of ancient civilizations. There are sort of main calendars. This is an example of a lunar calendar. This is the Chinese calendar. Well, not actually what the calendar looks like, but an example of a calendar that used the moon's orbit around the Earth as its main dividing line for time. Then you had solar calendars. This is a depiction of the Aztec solar calendar. So they used the apparent motion of the sun through the atmosphere in order to, not the atmosphere, through around the sky in order to demarcate the seasons and the years and months, right? So lunar and solar calendars are main types of calendars there. So the story that I'm going to tell here is largely a Western one, though. That's because it's in a lot of ways the way that our intellectual tradition has been framed in terms of the Greeks and Greek myths and Greek learning. I know that there are different stories told in the Chinese culture as well as in the Arabic culture, and a lot of these stories are happening simultaneously to this story, in a lot of ways inform this story as well. But we are kind of largely steeped in Western tradition, so I'll apologize in advance for advancing the norms of dead white men, but there we have it. So let's talk about the Greek aesthetic. You see here a sculpture from ancient Greece. And what we see in their art and their architecture over and over and over again are a few common things. The Greek aesthetic is just a nice way of saying a study of beauty or norms of beauty, or just a way of thinking is another way of thinking about the notion of an aesthetic. It's a mindset that informs how we perceive the world. So the Greek aesthetic, from their art and their architecture and their stories and their songs and their works of art, we see is largely framed around the idea of perfection, right? That we seek perfection. We see the Greek sculptures are all perfected human bodies. In art and architecture, clean lines, especially notions of symmetry. So symmetry is seen as perfect. And what's the most symmetrical object you have? Well, that's of course a circle. Circles and spheres are held up in high regard as being perfect objects because of their symmetry. And who is perfect? Well, of course, the gods are perfect. So there's this link between the Greek aesthetic of perfection and reverence of the gods. So that's an important thing. And it's important that we have that mindset because that's what the Greeks are looking for. And we see that all over the place. In their architecture, as I said, you have that. Here's another example down here of their architecture. What you have here is the golden ratio that you may know. So not only are circles and symmetry, but specific ratios are really important to the Greeks as well in terms of how they look for things and patterns in nature. For example, in the Parthenon, this particular golden ratio, you find that ratio all over the place, like the distance between here, between this height and that length are in a particular ratio, between this length and this length are in a particular ratio, and that ratio pops up all over the place. Now, where did they get that ratio from? Right from nature. The Greeks believed in perfection of beauty and symmetry. The perfect human face is perfectly symmetrical about a vertical axis, right? As well as the face should obey certain norms of the golden ratio. Like, for example, the distance between the eyes to the distance from the eyes to the mouth should be in a specific ratio. The length of the nose between the nose and the mouth should be a certain ratio. So there's all these different ratios that the Greeks think embody symmetry, ratios, and perfection. We hear that in Greek music as well, the tonal scales that they use. All the frequencies are in very specific ratios that all come from things like the golden ratio. So why is that important? It's important because if you think the gods created the universe, and you think the gods are perfect, and if you think the manifestation of perfection is symmetry, circles, and ratios, what you do is you go in when you're trying to do things like experiments, and you expect to see things like circles because that's how you've been programmed. Okay? So let's talk about some specific people. First off, Thales. Thales is actually thought of as the father of modern scientists in a lot of ways. Rather than a belief that physical events were caused by the actions of gods, he was looking for cause and effect within the physical world and wrote a number of texts that we still have access to where he explains those beliefs of looking for cause and effect in the physical world. It was profoundly influential for most of the Western tradition of science. Now, the reason why we care about Thales right now, though, is that he studied geometry, and a lot of our basic norms of geometry come from Thales. Specifically, he outlines what eventually would become trigonometry, specifically spherical geometry. Why is that important, spherical geometry? Spherical geometry is how we do astronomy. If I want to locate a star in the heavens, the way I do it is I face due north, and then I look for the star and say, well, how many degrees above the horizon is that star? And then I go from there. How many degrees left or right from that is that star? And I can create a location, quote unquote, in space based on an angle of elevation and then an angle left or right from that. And that's actually how we record data about stars still to this day. So that idea that Thales set out millennia ago is really important. Now, Thales had a very particular view of the cosmos. You'll see that here, this picture. He actually did think of the flat Earth at that time, with a crystal dome around it, and the Earth was floating on this waterbed. Now, the reason for that, by the way, was he was trying to explain earthquakes, and he thought if the Earth was floating on water, that would be a reason why we'd have earthquakes. Now, we know now that the Earth is floating, or the crust is floating on magma, but not quite right. But still, he had reasons for this. Now, this particular view of the cosmos was not widely accepted, but you can still see he did think the Earth was circular and the heavens were spherical. Right, so Thales. On next to the Pythagoreans. And I just wanted to kind of bring up some stuff about them. They were an interesting bunch of people. You know that they are responsible for, Pythagoras and his ilk were responsible for modern trigonometry and our understandings of triangle geometry, right? I bring them up because if you look here, they had a very unpopular belief. The general belief at that time period was that geocentrism was the way to go, that the Earth was at the center of everything and that everything orbited around the Earth. And why did people think that? Well, when you're standing there in the middle of Greece and you look up, you see apparently the sun moving across the sky, the stars move across the sky at night, the moon goes across the sky at night. So it seemed plausible to you, especially if you lived and died within about 10 miles of where you were born, that what your observation would be the truth. The Pythagoreans roundly rejected the existence of the gods and the gods' actions in our universe, as well as they actually rejected the notion of geocentrism. And for that, they were horribly persecuted. And that's actually a bit of a theme that we're going to develop over the course of the next couple of lessons here, is that when you go against the norms of the time, when you go against the paradigm, the aesthetic that people believe in, you get persecuted. The Pythagoreans were horribly persecuted, beaten and jailed and killed. In Sparta, if you were found out to be a Pythagorean, your hand was chopped off, your left hand was chopped off, it was shoved down your throat, your stomach was opened up, they put a rock in your stomach, then they sewed up your stomach, and then they threw you in a lake. A little bit of overkill, but the Spartans were kind of known for that. Why did they chop off your left hand? Well, the Pythagoreans were actually a cult, a math cult that came from Pythagoras. And the way that Pythagoreans would identify each other is they had a tattoo on their left hand. Not a very good way if you're trying to hide your cult, but there it is. But we still thank the Pythagoreans for their work in geometry, as well as their object lesson of what it means to go against the cultural norms at the time. So, Aristotle. Aristotle is so wrong, so very wrong. Aristotle did many great things, but everything he said about science was really, really, really bad for us in terms of advancing our norms. So what does Aristotle say wrong? He said that two objects drop, heavier things fall faster. We know that we ignore air resistance and gravity is the only thing acting, if they're in free fall, that those two things hit the ground at the same time. Aristotle said that you have to keep pushing on things or else they stop. But we know that that's not what inertia tells us, Newton's first law. because Aristotle couldn't imagine a world without friction, couldn't imagine a world without air resistance to look at base ideas. He was looking at what happened physically and said, that's what's true always. And that was problematic. For this story, Aristotle supported the geocentric model really strongly. He's actually the one that encodes that in a lot of Western canon in terms of his writing. Okay, and so Earth at the center, everything orbiting around. So you had the moon, and then the sun, and then the stars orbiting around that. So here's the thing: why was Aristotle so influential? Well, it's actually pretty clear reason why, and this picture reveals it. So this is the Greek Empire, but this is not what the Greek Empire always looked like. This is the Greek Empire in or after the reign of Alexander the Great. And you may know Alexander the Great conquered a large swath of land, and Aristotle was his tutor. And when Alexander the Great went and conquered all these lands, he brought Aristotle with him. And so what Aristotle did, one of his main influences was, as they were conquering all these lands, Aristotle told Alexander to build libraries in each of those places and to house all the knowledge of the Greeks in each of those places to spread those ideas. So by effectively spreading his understandings of the universe through these libraries and having those be persistent knowledge in those places that were teaching people those ideas, he was able to encode his understandings of the universe far and wide. Without Alexander, probably we would not venerate Aristotle in the same sort of way. So, moving on. A gentleman named Aristarchus. Aristarchus was a really interesting fellow there in the sort of 3rd century BCE. Aristarchus was doing his work at a place called the Library of Alexandria. It's one of those libraries that was set up after Alexander the Great. And so here's the thing about Aristarchus. People have this bizarre notion that back in that day and age, that people thought the earth was flat, etc. Even Aristotle, as wrong as he was, didn't think the earth was flat. They thought about a spherical earth. Aristarchus also believed that as well. And something that Aristarchus was able to do is actually he calculated the distance between the earth and the sun within decent accuracy for that time period, right? So they knew that distance. And I think people get this bizarre notion that, people from the ancients were backwards with astronomy. Even though they had some backwards notions like the geocentric idea, they were still able to know this number within about 5% of its present accuracy, which is incredible given how terrible their tools are. And the way that Aristarchus did, and we see this picture, which is directly from the only text that we have surviving from Aristarchus's work, shows how he did it. And what you see is that he's using similar triangles and is using the moon and the sun and eclipses, as well as creating similar triangles. What he does actually is he holds a coin up in front of the moon and holds a coin up in front of the sun, and he moves the coin until it occludes the image and then measures the distance between his eye and the coin, and then the diameter of the coin. And there's reasons why they actually know the diameter of the moon. They're able to get to the distance to the moon and then use that same method to get the distance to the sun. It's really impressive work for so far ago. So just similar triangles, right, is able to find out that distance. Now, I should note also, Aristarchus, even though we don't actually have the text anymore, there's writings specifically referenced by Archimedes later, who also studied at the Library of Alexandria and did his work there, where Aristarchus posited a heliocentric model in like 235 BCE. It's actually the first heliocentric model that we have record of. And you can see the sun at the center, and he had the right order of the planets at that time. At that time, they only knew of a couple of these planets. They didn't call them planets. I'll talk about what they called them in a couple of minutes. But I think this is super impressive. Now, here's the thing. Aristarchus wasn't persecuted, though, for this. He was just thought to be eccentric. The reason was because he worked at the Library of Alexandria. In that place, they fostered an ethic of questioning and scientific experimentation. So it was a safe place to have divergent views, right? Aristarchus wouldn't have rolled up to Sparta and said, hey, guys, this is what I think. But it goes to show what the norms of society allow in terms of questioning. Of course, not a lot of people believed Aristarchus's model. So in the realm of people who figured out pretty impressive things in that same time period, in also the 3rd century BCE, Eratosthenes is able to actually find out the radius of the Earth. So they knew how big the Earth was. And the way he did that, once again, he also worked at the Library of Alexandria, is he noticed that on the summer solstice, which is the longest day of the year, that there was this obelisk, which is like a giant tower, like the Washington Monument, that cast a shadow at noon. But on the summer solstice at noon, the sun is supposed to be directly overhead, so it shouldn't cast a shadow. But it cast a shadow. But Eratosthenes had read that at this place called Syene, which was south of him in Egypt, that an obelisk on the summer solstice, didn't cast a shadow. That's because the sun was directly overhead, because this city was on the equator. And so what he is able to do is, once again, similar triangles. By knowing the length of the shadow and the height of the obelisk, you can see this triangle here. Now, it's not perfectly a triangle, but this is a very small triangle. So you can imagine that curvature is very little, because we're talking about the shadow of an obelisk on the ground. The curvature, it's not going to matter. So this triangle to this particular triangle ends up being a similar triangle. And so all he has to do is pace off the distance between these two. And so now he knows this, he knows that, he knows the height, and therefore he's able to know what the radius of the Earth is. And Eratosthenes' calculation is within 3% error of accuracy of what we now know today. And that was probably more due to the measurement error about the uniform length of a pace, which is what they were using as their measuring tool between here and here. Brilliant work done for that time period. So in that time period, they may have thought that the heliocentrism was the way, or excuse me, geocentrism was the way to go, but they still knew things like the distance between the Earth and the Sun, the Earth and the Moon, the radius of the Moon, the radius of the Earth, which is really fantastic stuff. Now we come to it. Ptolemy, just after first and second century AD. Ptolemy is known as the father of the father of geocentrism. That's not because other people didn't posit geocentrism. We talked about, Aristotle setting that out. Ptolemy is called that because he takes all the work of all the Greeks on geocentrism and writes this book called the Almagest that puts together all the data and all the ideas to create the definitive understanding of what geocentrism looked like. And he has all this data from all these astronomical observations and these equations for predicting things like, based on the model, when lunar eclipses would happen, solar eclipses would happen, when certain stars would be in certain locations. There were tables and equations and formulas. So it's a really one-stop shop for prediction of astronomical events. And then you might notice this Almagest, a word that sounds like that in modern day, a book that talks and makes predictions about physical phenomena. You may know that as an almanac. The Almagest was the first almanac. So it explains the geocentric model, and we see that here. The Earth is at the center, then the Moon, then Mercury, Venus, the Sun, Mars, Jupiter, Saturn. There's reasons for that particular order. But here's the thing. And then the stars on the outside. The Mercury, Venus, Mars, Jupiter, and Saturn, they actually thought those weren't planets. They thought they were stars. And the reason is because if you look up into the sky, with the naked eye, they do look like stars. But they called them something called the wandering stars. And that was because if you go out at night and you point at a star at, say, midnight, and then you look the next day, like let's say the Vega or one of the stars in Orion's belt, and you point at that. If you go out the next night at midnight, that star has moved a little. It's not in the exact same space. You go out at night and you track the star across the sky, and that star will move a little bit across the night sky at midnight every night until you can no longer see it, if it's not one of like the pole star, right? So it looks like the stars are moving through the night sky. The stars that look like Venus, Mercury, Mars, Jupiter, and Saturn, if you do that same thing, you look up and it looks like it moves forward, forward, forward. Then it starts to seemingly move backwards, 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 then forwards, then backwards, and forwards, and backwards, and forwards, and backwards across the night sky, which is why they were called the wandering stars. In Greek, the word for wanderer is planektos, which is actually where we get the word planet from. So Ptolemy is trying to figure out like what's causing that backwards and forwards motion across the night sky, and he comes up with something called the epicycloid. So what he says is that those wandering stars exist on a circle, right? And that circle is on another circle. Because it's super important that, remember, we said that the Greek ideas, they were looking for circles. Not just circles, but circles with constant speeds. Everything was thought to move in perfect circles at constant speeds, because that would be perfect and symmetrical and fit the Greek ideal best. And so what Ptolemy is saying is that the planets move on these little circles as these circles actually themselves go around. So what does that look like? That ends up looking like this. So they thought that these wandering stars follow these curly Q patterns here. And later, if you want to see that in action, you can click that link and then go to a website that'll show this in action, right? So as this green dot goes around this circle, but this red circle orbits the Earth, you end up with these paths. So this is where they saw, let's say, Mars going forward, 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 and then backwards, backwards, forwards, 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 and then backwards, backwards. This seeming backwards motion of the planets was known as retrograde motion. And so they thought that Mercury, all the planets, showed this retrograde motion. So we'll talk about later what's actually causing that. But the great thing about the Ptolemaic model is that, you know, using his tables and his data and this model, as weird as these epicycloids are, which is what these are called, these curly Q patterns, the predictions are pretty good, right? And that was the importance of the model, was to make predictions for events. So because the predictions were pretty good, people were kind of like, okay, that confirms the model. It does what we need it to do. It allows us to make predictions. It seems stable, and it fits within our aesthetic. And so those aesthetics were super powerful because, I mean, would you ever think to look for this pattern? No, but if you think I need to find circles, this solution elegantly, mathematically creates everything you think you're looking for and fits the evidence that you have to a pretty good degree. So from there, we're going to be moving forward into the more modern era. So I'm going to just stop this video now, take yourself a little break, and then we'll come back and talk in the next video about the modern era.